Relationship between zeros and coefficients of a quadratic polynomial. Hello everyone. Before we dive into today's new topic, let's take a quick look back at what we have already covered. In our previous lessons, we focused on the mechanics of finding the zeros of a quadratic polynomial, specifically by using the method of factorization to break down the expression. Now, moving into this new subsection, we are going to explore something much more powerful, a fundamental algebraic property. We aren't just looking for the zeros anymore. We are going to uncover the direct relationship that exists between those zeros and the coefficients of the polynomial itself. You might be wondering, why does this matter? Well, understanding this connection is incredibly useful. It gives us a built-in way to verify if the zeros we calculated through factorization are actually correct. Furthermore, it provides us with a deeper insight into how the polynomial behaves, allowing us to understand its properties even without the need to fully solve the entire equation. Let's get started. Understanding the quadratic polynomial. To begin, we need to define what a general quadratic polynomial actually looks like. We express this mathematically as p of x equals a x squared plus bx plus c. To understand this expression, we need to identify its components. First, we have a, which is the coefficient of the x squared term. It is very important to note that a cannot be equal to 0, because if it were, our equation would no longer be quadratic. Next, we have b, which is the coefficient of the x term. And finally, we have c, which is our constant term, the part that stays the same regardless of the value of x. Now, moving forward to the next part of our lesson, we need to talk about the zeros of this polynomial. If we call these two zeros alpha and beta, these are simply the specific values of x that, when plugged into our polynomial, make the entire expression equal to 0. In other words, they are the solutions where p of x equals 0. Keep this definition in mind, as we are about to see how these zeros relate directly to those coefficients, a, b, and c, in the next slide. Now that we've introduced the topic, let's take a closer look at the structure of the polynomial we'll be working with. The core relationships. Now that we have defined our general quadratic polynomial and identified our two zeros, alpha and beta, let's look at the heart of today's lesson. As you can see on the slide, there are two primary mathematical relationships that directly connect these zeros, alpha and beta, to the coefficients a, b, and c that we identified in the previous slide. First, let's look at part A, the sum of zeros. This formula tells us that if we add our two zeros together, the result is equal to the negative ratio of the coefficient of x to the coefficient of x squared. In mathematical notation, alpha plus beta equals negative b over a. To put this in plain English, the sum of alpha and beta is equal to the negative of the coefficient of x, all divided by the coefficient of x squared. This is a very powerful tool, because it allows us to find the sum without even knowing the individual values of the zeros. Next, we have part B, the product of zeros. This relationship is just as important. It states that the product of our zeros, which we write as alpha times beta, is equal to the ratio of the constant term to the coefficient of x squared. In notation, alpha beta equals c over a. Simply put, you take the constant term, c, and divide it by the coefficient of the x squared term, a. Keep these two formulas in mind, because in the next slide, I am going to show you a step-by-step process on how to use these exact relationships to verify your answers during an exam. Step-by-step verification process. Now that we have understood the theoretical formulas for the sum and product of zeros, you might be wondering, how do I actually apply this in an exam or a problem set? Well, on this slide, I will walk you through a systematic, four-step verification process that you can use every single time. First, your very first step is to identify the coefficients. Look closely at your given polynomial and clearly write enough the values for a, b, and c. Be extra careful with the signs here, as we will discuss later in the lesson. Second, you need to find the zeros. Using the skills you learned in our previous lessons, use methods like factorization or the quadratic formula to solve for the polynomial. Your goal here is to find the specific values of alpha and beta. Third, we move to calculate the sum. Once you have your values for alpha and beta, add them together. After you get that total, compare it to the result you get from the formula. Negative b divided by a. If these two numbers are identical, you are on the right track. Finally, the fourth step is to calculate the product. Take those same values, alpha and beta, and multiply them. Then, compare this product to the value of c divided by a. If both your sum and your product match the formulas perfectly, as you are about to see in the upcoming examples, then you have successfully verified the relationship. Illustrative examples. Now that we have understood the theoretical formulas for the sum and product of zeros, let's put them into practice with our first illustrative example. We will look at a standard algebraic polynomial, p of x, which is equal to x squared minus 5x plus 6. To see if the relationship holds true, we are going to follow a systematic four-step verification process. Step 1 is to identify our coefficients. Looking at our polynomial, we compare it to the general form we discussed in the previous slide. Here, the coefficient of x squared, which is a, is 1. The coefficient of x, which is b, is negative 5, and our constant term, c, is 6. Step 2 is to find the actual zeros of the polynomial. We will use the method of splitting the middle term that you are all familiar with. We rewrite the middle term, negative 5x, as negative 2x minus 3x. This gives us x squared minus 2x minus 3x plus 6 equals 0. Now we group the terms to factor out common elements. X times the quantity x minus 2 minus 3 times the quantity x minus 2, which simplifies beautifully into the product of the quantity x minus 2 and the quantity x minus 3, all equal to 0. From this, we can clearly see that our two zeros, alpha and beta, are 2 and 3. Step 3 is to verify the sum. First, let's calculate the actual sum of the zeros we just found. 2 plus 3 equals 5. Now, let's apply the formula we learned on the previous slide, which is negative b over a. Since b is negative 5, negative b becomes positive 5. Dividing that by a, which is 1, gives us 5. As you can see, the actual sum and the formula sum are identical. Finally, in step 4, we verify the product. The actual product of our zeros, alpha times beta, is 2 times 3, which equals 6. Using our formula, c over a, we take our constant term, 6, and divide it by a, which is 1, resulting in 6. Once again, the values match perfectly, confirming that our zeros are correct, and the relationship between the coefficients and zeros is verified. Illustrative examples continued. Now that we have seen how this works with a standard algebraic expression in our first example, let's move on to something a bit more practical. In this second example, we are going to look at a real-world application involving projectile motion. Imagine you throw a ball upwards into the air. In physics, the height of that ball at any given time can be modeled using a quadratic polynomial. Let's say the height, which we'll call h of t, is given by the equation negative 5t squared plus 20t plus 25. Our goal here is to find out when the ball hits the ground. Mathematically, the ball hits the ground when the height is 0, so we are looking for the zeros of this polynomial. Let's follow the same four-step verification process we used in the previous slide. Step 1, identify the coefficients. Looking at our equation, we can see that it equals negative 5, b equals 20, and c equals 25. Step 2, find the zeros for time t. We start with our equation, negative 5t squared plus 20t plus $2025, and set it equal to 0. To make this easier to factor, let's divide the entire equation by negative 5. This leaves us with t squared minus 4t minus 5 equals 0. Now we can factor this quadratic into the product of two binomials, t minus 5 and t plus 1, all equals 0. This gives us two zeros, alpha equals 5 and beta equals negative 1. Now, a quick note here. Since we are talking about real-world time, we would ignore the negative 1 because time cannot be negative. However, for our algebraic verification, we must use both values. Step 3, verify the sum. Let's calculate the actual sum of our zeros first. 5 plus -1 equals 4. Now, let's check this against our formula, which is negative b over a, that would be -20, divided by -5, which simplifies to 4. As you can see, the values match perfectly. Step 4, verify the product. First, the actual product of our zeros is 5 times -1, which gives us -5. Now, let's use the formula, which is c over a, that is 25 divided by -5, which also results in -5. Once again, the values match. This confirms that our calculated zeros are correct. In the next slide, I will point out some common pitfalls to watch out for when performing these calculations yourself. Common mistakes to avoid. First, let's talk about the sign error in the sum. This is perhaps the most frequent mistake students make. Remember, the formula for the sum of zeros is negative b over a. Because of that negative sign in the numerator, you must be extremely careful when b itself is a negative number. For instance, if b equals -5, then negative b becomes -5, which simplifies to +5. Always double-check that you haven't missed that extra sign flip. Second, watch out for incorrect coefficient identification. When you are looking at a polynomial, you must include the sign attached to the number. If you see a polynomial like p of x equals 2x squared minus 3x plus 1, do not simply say b is 3. You must identify b as -3. If you ignore that minus sign, your entire verification process will be incorrect. Finally, try to avoid confusion between a and c. It sounds simple, but in the heat of solving a complex problem, it is easy to swap them. Just keep a steady focus. A is always the coefficient attached to the x squared term, and c is your constant term, the number standing all by itself. Now, before we wrap up and look at our final summary, I want to pause and discuss some common pitfalls. Even if you understand the formulas, it is very easy to make small errors that lead to the wrong answer. Keep these 3 points in mind, and you will find that verifying your zeros becomes much more reliable. Now, let's move to our final slide to summarize everything we have learned today. Key takeaways. Remember, for any quadratic polynomial in the form a x squared plus bx plus c, the two zeros, which we have called alpha and beta, are directly and fundamentally linked to the coefficients a, b, and c. As we saw in our core relationship slide, there are two specific formulas you must memorize. First, the sum of the zeros, alpha plus beta, is equal to negative b divided by a. Second, the product of the zeros, alpha times beta, is equal to c divided by a. As we demonstrated through our step-by-step examples, these formulas are incredibly powerful. They provide you with a quick and efficient method to verify your work. Once you have found your zeros through factorization, simply plug them into these formulas to check if they match the coefficients. If they do, you can be confident that your calculations are correct. To wrap up our lesson today, let's quickly recap the essential points we have covered. Keep these relationships in mind, as they are the foundation for much more complex algebraic work ahead.